Now, coming back to the topic, this topic I think is very interesting because these days the new technologies are being developed everywhere, and especially for the design of infrastructure. And as we know, that the physical infrastructure is the backbone of any economy, any society. All the development that we showcase is kind of reflected in the infrastructure that we design, build, and operate. And out of that infrastructure, we can see that the technologies, the evolving technologies will be very important when we design and manage these infrastructure in the future. And out of that infrastructure, I think the main part is that we have to make sure that we make the process, we use the technologies to make this process efficient, the design and the whole management of the infrastructure, and also we create a better solution by using integrated tools and digital integration. And at the same time, we can do things that previously we were not able to do effectively while using the traditional or the manual practices. Now, if you look at the impact of these advanced technologies in infrastructure, or in fact in many other fields, we can look at three key aspects. The first one is that the integrated design workflow. So the digital streamlining of the process can help us to improve the design workflow and connect various steps digitally. Second one is to cater for greater life cycle phases of a project. As you know, every infrastructure project goes through many life cycle steps. And if we have a digital management of the information, then they can be integrated well. And the last and the more important one is also that we can communicate our design better to the public and also between various professionals. For that, the key technologies that are now affecting all of this work, we can summarize them in AI. Of course, we all know that there's a big impact of AI right now. Building information modeling and also the bridge information modeling, BRIM, both of them are important. The parametric design is very critical because now we have moved from the traditional drawing-based models to parametric models. And then visualization of those models using digital technologies as well as collaboration with others. So these are the key technologies that are shaping the future of infrastructure design and more importantly, the bridge design that is the focus of our talk today. Now, bridges, as we all know, are essential, in part of the infrastructure. In fact, probably one of their most visible part of infrastructure, both symbolically and functionally, because whenever we have, to cross any river, or we have to construct the elevated expressways and so many, or even for the waterways, we need bridges. So bridges are a very important component of a physical infrastructure. Now, bridge project is a complex one, like any other project, but I just want to spend a couple of seconds on this one. So bridge project, if you look at the project, we have to look at the construction method, the life cycle, the structural forms, the material, components, stakeholders, use of the bridge, and analysis and design, which is the main function of the structural engineers. And each one of them can further be expanded into more specific types. So if you look at the entire project, it's pretty complex, and it is not practically possible to integrate or develop tools that will handle all of the bridges, of all of the materials, of all of the types, for all of the stakeholders. So that just the system will become not only very complex, but not usable because not everybody is handling all the steps at the same time. So that's why we will focus on application of the technologies on a specific type of bridge here, just to demonstrate how they are applied. Now, before we do that, let me quickly take you through the typical life cycle and phases of a bridge model, how it is developed. And you can see from here that we start the bridge with the planning and feasibility studies, site investigation, preliminary design, environmental impact assessment, and detailed design, many approvals, construction, quality control, management of the bridge, and operation, and as well as inspections and assessment. And finally, we may have to do some rehabilitation and end of the life. So it's a long, over 100 years, maybe spread over 100 years or more. So the bridge life cycle is pretty long, and most of these steps are integrated and handled by the agencies responsible for maintaining infrastructure. And the design process, we can see that there are so many people involved in this one also. So for the professionals that are involved and the stakeholders that are involved at every step are many, and all of them need to have access to information, and all of them they add to the information, they use the information for previous life cycles, and they communicate, and they do their own part in the overall project. So traditionally, there's a lot of documents that are shared both in printed form or in different documents in Excel, in Word, in AutoCAD, and in analysis models and in financial models. But ultimately, the information needs to be integrated. And now that we have this digital era, it's a great opportunity for us to build the entire information from a single model. So to do that, I want to demonstrate this on a simple bridge first. And we are going to take the example of a concrete I and T girder bridge, which are very common. As you can see, when you travel around, you see these bridges, especially in rural areas and even in urban areas where they are used to build expressways and also waterways and so on. So we can see many of those. Now, if you look at the design workflow for a typical bridge, you can see that we start with the alignment. That means it is given by the highway engineers. Then we have a design brief for the bridge. What kind of bridge? What do we want for this bridge to look like? Then system selection, and that is very critical part. How do we choose the right system for that bridge? How many spans should we use? What girder types we should use, and so on. And then we create a bridge model as a structural engineer and the bridge engineer. Then we do the preliminary design of the components. Then we do a detailed design. Then we do the detailing, reinforcement detailing, and joint detailing and connection detailing. And then we communicate this information to the authorities, to the other stakeholders, to other professionals, and then we get the design approvals, and finally the construction documents are made and the construction commences. So I'm looking at this design process, this workflow, which we can digitally integrate if we have the right information to start with. To do that, I will take the example of a new program that we have launched next month, and this is called CSI Bridge Express. So CSI Bridge is an existing program. In fact, it was developed about 20 years ago by Computers and Structures Incorporated in US, and now we are working on the second generation of this program. In fact, adding on to that one, which is called Bridge Express. And Express means that this is basically the workflow is faster and smarter, and these two programs can work together. They're about 20 years apart. This was in 2004, and this one is in 2024. So we can see how the technologies have changed. So let me start with this one. The first thing that we need to do for this to happen is we must have a geometrically complete model. Normally, structural engineers start with a structural model, and that is not good enough to handle all aspects of the design because it doesn't have all the information. They only have the information necessary for analysis, which will be simplified and may not represent the physical character of the structure. So we should start with a parametric definition of the bridge, and that's the important part. So what I'm showing here is that how you can define each component of the bridge using basic parameters, and then gradually use them to build up more complex components. So starting from the capping beam to the column, and then you build up the bends, and then you add the foundation. Various types of foundations can be modified. You can change the parameters, and everything gets connected. So this parametric modeling is now quite common. There are many tools available, but here, instead of using external tools, we basically embed all of the parametric modeling into the program. So that's the first thing. The next one is that we use that information to create the whole bridge. So we can standardize those components, and we can save them into libraries so they can be reused. And that is the biggest advantage of parametric components, that once they are defined, they can be used across projects, across departments, across countries, across the various consultants, because ultimately there are not a lot of variations in a most typical bridges. Of course, there are special cases where they can be modified. So if a department is responsible for designing these bridges, they can accelerate the design considerably by standardizing them and saving them into the libraries, and then those libraries can then be used in the bridge. So like for example, And then you can also add, more importantly, in the parametric definition, we can also add the reinforcement right from the beginning. This is a major change from the traditional design workflow where we wait for the analysis and design to be completed until we decide on the reinforcement. But as we know, most of us, we are involved in the design for a long time. We know that the reinforcement cage is basically a property of the component, and mostly it is governed by basic detailing rules. It is governed by the geometry. It is governed by the practicalities and the practices, construction practices. And of course, the reinforcement size, bar, diameter, spacing will change, but the basic configuration will not change much. So that's why we have added the reinforcement right into the component definition, so they are available as soon as the bridge component is defined. Reinforcement is all directly available. And then we can use all this information, the parametrically defined model components and the standardization, and then we can construct a full bridge model very quickly by simply selecting the appropriate components on an appropriate alignment. And we can just select what type of bend we use, and then what kind of bend cap we will use, what kind of foundation we will use, because it's all been defined and stored as parametric components. So we get the parametric models, and then you can see from here the abutments can be modeled, and we can complete the bridge by simply changing a few parameters. This helps us to create a typical bridge in less than 15, 20 minutes with a standard bridge. Of course, complicated bridges can be edited later, but most typical bridge will take a few minutes, less than an hour in any case, to create the model. And this is a much faster way than defining the models individually. So you can see it from here. And another advantage is that once we create these parametric models, as you can see here, they're geometrically very, very complete in the sense that they incorporate all of the construction details right from the beginning. So, and they are transferred to the structural analysis model. You can see from here that we are modeling the bearings and the girders and the variations and the expansion joints and the half girders and everything, and then that goes to the analysis shell model or the solid model right on the right hand side, which is geometrically consistent and complete. And this is a big advantage of using geometrically consistent starting parametric models. And then we can have a whole bridge model, which is on the top, which is as you can see, is rendered nearly physically complete model, and as analysis model which matches with that, which is automatically generated from the geometric model. And that's the advantage of using this parametric and geometric model approach. Now, because of this one, we can improve the workflow. And we can see from here that now the first thing that will help us now is component reuse. And I mentioned that we can define the components, and then we can create libraries, and there could be the whole library set for each type of bridge for several columns, and we can just store them and those libraries can be shared. And then, for example, we create a special type of foundation for this bridge, and then we export it and save it into a library, and this library now becomes available for other people to use. So we can save that, we can see what are the components that we are going to save. We save the library here, and then we can start a new project, and then this is a new project, different project, and we bring in those components, and just from the file, and then you say, okay, I want to use this component, and I want to use the bends from there, and then you drag and drop those bends into the new project here. This is a different project, as you can see. It's a flyover, U-turn flyover, and then you select the component that was defined for another project, and then you just drop it there, and then that component is updated. So this way, the component reuse can significantly improve the design process. And then another important thing is the layout. I mentioned that the workflow starts from the layout of the bridge, and if we have the ability to import the ground information, the site information, the layout information, and many programs have that, we can bring in the layout, and then we can simply place the bridge, which we can make a straight bridge first, and then just drop the alignment there, and then the bridge will adapt to that alignment automatically. And that is a great advantage, because we can create complex layouts very easily by first creating a straight bridge using these stations, and then just apply it to the alignment, and then automatically the foundations will be laid out under the ground. The ground profile can be extracted from there, and you can see from here the ground profile and the foundation layout can be done automatically. So this saves considerable amount of time in terms of creating the bridge models, and we can assign the geotechnical properties at each location, and from those geotechnical properties will be automatically used to generate the soil springs for the modeling of the foundation and the soil structure interaction. So now let's look at the complete design workflow and in a summary and how this will work. So let's see that we are starting with a model, and then we from the ground, and then we create a model from there. And this is a very complete rendered model created in the same program and with the textures and all. And then you create a structural model from there automatically. The program will do that, and then we run the analysis, and you get the stresses and all of that. And from the stresses, we integrate the stresses to get the response, which response, bending moment and shear forces that are needed for design. And then we do the design, we get the bending moment, let's say on a bend, and then from that we can calculate for the columns, we can do the interaction diagrams, we can calculate the forces, we can calculate the capacity ratios, and then from there we can determine the reinforcement or update the reinforcement which is already there. And then from there we can go to creating a full rebar cage. And this is a huge advantage, because after we place the design, the entire reinforcement cage in 3 dimension is already available, and it has already been updated based on the actual design parameters, and that will save considerable amount of time. And then from there, we can transfer it to Revit or IFC for further communication or modification. And this is once again very important part, as I mentioned, communication. And then we can also send it to the CSI Bridge main, because I mentioned to you we have 2 parts of the program: the existing program, the big one, and this new tool, and they are integrated together. We can also create VR, virtual reality models from there. And this is, I want to mention here that because our model is geometrically complete, we don't need a third-party tool or another tool to create a geometric model that will be suitable for virtual reality or augmented reality or mixed reality, because this model is already good enough for that. So we create those models, and then we can create the summaries of the reports, and for the site layout, we can then also create from that the layout. We can send it back to Google Map, and then we can place the bridge onto the map where we started from. So it's a map-to-map full integration in one workflow, one workflow in a single tool. I also want to mention that we can also get a very detailed calculation from the report with all of the formulas and the things of the engineers who want to submit this for approvals. They can directly submit the approval detailed calculations from that, and also more importantly, they can create the bill of quantities and cost estimates. And this is so, which means it has now complete all of the items in the workflow are now complete. I want to mention that this BOQ actually can be created without going through the entire project, because the reinforcement and the sizes are already available at the beginning. So a preliminary cost estimate, a preliminary BOQ could be created, which could then be updated and modified after the design cycle is complete. So this gives an opportunity for the engineers and for the departments and for the stakeholders to get a quick estimate of the bridge. So that is the complete workflow that I mentioned, that this digitization or bringing in many tools can help to streamline and to make this much faster. So I just mentioned that we can have the BOQ before the design, and we can also have the BOQ after the complete design. I just want to emphasize this part because this is a very important advantage of using this kind of digital models. And design communication, this is another part that mostly engineers are lacking, because our designs are not complete enough for the public or other stakeholders to make use of, because we are using structural models, shell elements, frame elements, load cases and all, which is not appreciated by other people enough. So in this way, because we have a parametric model, we can actually do much easier collaboration by, first of all, we can just export the model to various formats like IFC and Revit and so on, so people can import them into their system, and this will be completely geometrically complete models which they can use and on their own size. So if you export that and open it in any of the IFC viewers, in this case, you can see here that the model looks complete. So that geometric model completely came into IFC, and then from IFC, it can transfer to any other software that supports IFC standards. Similarly, we can collaborate the model through Revit, and Revit is as a popular tool similar to IFC. We can export the model to Revit, but the important thing is that these parametric elements can be now edited in Revit and brought back, because Revit also has the ability to define families and do parametric modeling. So our parametric modeling is integrated with the Revit parametric modeling through our own families there. So people can communicate and they can create the elements either in Revit or in our program and then communicate with that. So this is a major enhancement in terms of the Revit integration. So you can see from here that we can modify something and we can bring it back to the next one is the sharing of the models. One of the key problems that sometimes as engineers we have is that we do all these fantastic modeling in our tools like SAP or ETABS or whichever model we use, or CSI Bridge, but we can't communicate those models to other people who don't have that software, and they cannot appreciate the work that we are doing. So what we've done is that we can, in this tool, you can simply share a model, a link or a QR code to anybody, and they can open it on a web viewer, so they can see what you see. You can also share the reports, so they can actually physically interact with your model that you have created, and they can comment on it. And so this is a great way to share, to communicate, and also get feedback from stakeholders who may not know how to use this program or may not have this program with them. So that's a big advantage in collaboration and in communication. The other one is as I mentioned to you, that we can bring the models back to the Google Earth, and that is mostly to communicate the final design to the public, so that or to other stakeholders to see how this bridge will look like in the real environment, because now we have this Google Earth platform where everything in the 3 dimension can be viewed, and their buildings and other things are already there. So if you create your project and it's already a 3-dimensional parametric fully complete model, it can simply be placed back onto the let me just forward this so we can see that the model can ultimately be transferred to Google Earth, and we can then see it finally. And there is the model that we created onto the Google Earth, integrated with the rest of the information. So this will help us to communicate our design with the stakeholders, and also check how it will fit with the rest of the infrastructure. Enhanced visualization is very important, because once again, as I mentioned, we have a very detailed model and we have digital tools. We have so many now opportunities to create enhanced visualization, which we can see the model more clearly. So for example, we can do the model in textured view, in the rendered view, in terms of we can zoom in and we can see the bearing, we can see other details, because they're all modeled physically complete. And the next one is the use of the virtual, mixed, and augmented reality. Once again, when we see, we can transfer these models into any of the VR, AR, mixed MR tools by uploading them to the servers, and then we can use Google, any of the devices. So many devices are available these days to interact, and you can see the rebar cage, and people can actually physically interact, select, and also comment on these things. And in a real VR cave, this could be done between a group of engineers or group of stakeholders, where they can communicate through this immersive environment. And we can also do a 3D printing of the same model, because once again, as I mentioned, that this is complete model. So we can just select any component or the whole bridge, and we can do a 3D printing, and we can physically interact with that model. And this model then can be sent to any of the 3D printing devices. So, and this can be then sent to any of the 3D printing devices, as you can see here. And now 3D printers have become, very comprehensive. They can print the whole models in different scales, different level of detail. And so we can study physically, see how the static looks like, how the components look like and fit together. We can also use the reverse process now, using the LiDAR and drone images, to bring the model back. And this is one of the research done at AIT by one of the doctoral students. And so she actually used the LiDAR scans and the drone images to back construct the the digital twin, and then use that to do the structural health monitoring, and also create a SAP model from that to do the integration. And because now we have parametric models, so the LiDAR models can be directly converted into physical model through AI, interpretation, and also by physically connecting them together. And so this is where you can see the LiDAR model can be then converted into sort of a cleaned up model, removing unnecessary parts, and it can probably give us the parametric model directly from the LiDAR model. So this is an ongoing research that we are doing now to be able to. So this will help us a lot in documenting and creating models, digital models of the existing structure by simply using LiDAR or drone scans and getting a properly parametric model which can be used for other purposes. Now, the last item on the list, of course, is AI, and AI is everywhere. So we cannot sort of ignore in our profession. So AI can be used in a number of ways in the bridge, in structural design and anything, especially talking about the bridge design in the current context today. I'm going to present 3 ways that this can be used. The first one is that it can do the help, ask me kind of a thing, like the ChatGPT or other language models. So it is trained on the documentation of this program so that it give you specific sort of detailed answers to your queries, going through all of the documentation and the program itself. So you can ask many questions. It can give you a relevant answer to that. For example, what types are available, what I can do. So instead of giving you just the link to the help topic, it actually summarizes and helps you. So this is a good learning tool and also a quick way to get the information that you need without having to read a lot of irrelevant information. The second one is the prompt-enabled UI. So one of the things that because it's a parametric model, so we can use natural language instructions now instead of entering the data individually. So we can, for example, say change this type, and it will done, and it'll say change the number of bars from this one to this one, and we type it as a text prompt, and it will find the appropriate parameters, put the data, and update the model. So that's the big advantage of using this AI, that we can use the prompt-based editing now, and this will really help a lot because the people don't need to get trained in the program use and not have to learn how to do things. They just have to type, and the program will find the appropriate data and update that. Now, let me look at the last item on this presentation. Is like the application of AI, similar to what an experienced engineer would do. It's like a back of the envelope kind of a design. If you're in a hurry, then you can create a quick model using all AI prompt without doing any work on the program itself, and get a basic design done for a quick answer or preliminary design or cost estimates and something. So let's look at this example. So basically, here we are going to start with the new project and select the appropriate codes, and then say, okay, I want to start a project in which you will say that, okay, I want to give me a bridge with this much length, with that many lanes, and give me the most appropriate number of spans and the number of girders. So the program based trained on previous data will then find the appropriate structural system to fit this width and the length of the bridge, and come up with a basic design of the deck. So that will be the first part. So the deck design is done. The next one is that now we can then also continue to say add the support. So if we, now the superstructure is done, which is, based on AI training. And then you say, okay, I want to add this kind of support there. So the supports are added. Once again, we are not interacting with the program, just adding the prompt. And then we say, okay, now add the abutments, and you select just type the type of abutment, and it will fit the abutment to the bridge that you have already done. And after that, you say, okay, now let me see. I want to change the alignment to be a curve. This is a curved bridge, not a straight one. You just instruct the program, change this to a curved bridge, give the radius of the curve, and then we should have the bridge curved in that way. So now we have the curve. And let's say it's a ramp and it's also a slope. So we can go ahead and change the profile of the bridge and say, okay, elevate the bridge on the right-hand side by a certain meter. And so once again, it's just all happening through a prompt. And then combining the AI training plus the prompt-based editing plus the model generation, we can now get very quickly a bridge model in less than 3-4 minutes. This is real time. almost. So we don't, this is how much time it will take to create this model. And once the model is done, you should be able to run it. You should be able to design it. You should be able to get the view cube. You should be able to do everything on this one, because the rest of the process is pretty automated on this one. So you can get the bridge response. They can see the bending moments. You can get the initial period, frequencies. So without touching any of the data, using mostly AI, we are able to get the BOQs and the layout and the cost of the bridge in less than 5 minutes for a quick design. And that is what we were trying to mention in the beginning, that we can accelerate the whole process of the bridge design workflow using various technologies through digitally integrating everything. So I hope this information is of interest, and you're most welcome to send us comments. Thank you so much.